That's pretty rare for you to see that. Wow, we're really witnessing something historic here together. Welcome back to Chapter 18. We're going to continue building our derivative rules. In this particular video, we'll look at sections f and g. I think it makes sense to do exponential and logarithmic functions together. Let's take a look at two exponential functions. Here we have 2 to the power of x and 3 to the power of x. And I want to imagine what their derivatives might look like. So 2 to the power of x. As we move farther to the right, the slopes of the tangent lines are increasing towards positive infinity. As we move farther to the left, the slopes of the tangent lines are still positive, but are decreasing towards 0. And you know, we could actually say the exact same thing about the y values of this particular graph. And that's peculiar. That's not usually the case if we were to consider really any polynomial function, so like x squared. As we move farther to the right, both the y values and the slopes of the tangent lines both increase towards positive infinity. But as we move to the left, the y values increase to infinity, whereas the slopes decrease to negative infinity. If we were to consider a constant function, such as y equals 3, as we move to the right and the left, the y values are always 3, but the slopes are always 0. So in most cases, and you could make up a bunch of other examples if you wanted to, but in most cases, the slopes behave very differently from the y values of the original function. But with this exponential, and indeed with all exponentials, that's not the case. They actually do behave similarly. So let's take a look at its derivative. All right, its derivative sits a little bit below the graph. We've actually taken the original graph and vertically shrunk it. We've actually multiplied 2 to the x by some constant to get this new derivative. And we can talk about what that constant is later on, but just connecting this back to chapter 5 for a moment, hopefully you can see that vertical shrink. And what this says is that at any point along 2 to the x, if I were to choose any point there, the slope of the tangent line is a value that's less than the y value at that point. Okay, maybe not so interesting yet. We could look at 3 to the x again. Now 3 to the x is a little bit steeper than 2 to the x, right? So let's take a look at its derivative. Its derivative is a little bit above the graph. So at any point along 3 to the x, the slope of the tangent line is just a little bit more than the y value at that particular point, which raises the question now, is there any particular function whose derivative is exactly the same as the original function? Well, we can experiment with that here. Here's b to the power of x. Right now b is set to 1.55. Here's its derivative. It's down less than the graph. It's below it. As I increase the b value, so now we've just gotten a little bit above 2, my derivative is getting closer and closer to the original graph. And right around here, as I get close to 2.7-ish, they're getting very, very close to each other. Now there is a very special number that's right around 2.71828, and that number is e. So it turns out that e to the x is its own derivative. There's a proof in the book if you'd like to read through it, but I just wanted to focus on the visual magic of that. Like that makes e a very special number. If you didn't think that e was important before calculus, you just thought it was like some number that showed up with exponents for some reason, this is where e starts to really shine. It's its own derivative. That's cool. So rule number 1, this is in the data booklet, by the way, right there. The derivative of e to the x is e to the x. There it is again. What's not in the formula book is this right here. So we need to remember that every derivative rule we learn, we need to extend it for the chain rule. So when my function is e to the x, the derivative is e to the x. When my function is e to something else, My derivative is e to the something else multiplied by the derivative of something else. It's just chain rule. Rule number 2, down at the bottom. This is also in the formula book for any other exponential function. So here, written as a to the power of x. The derivative is a to the power of x multiplied by the ln of a. So in our previous 2 examples, we had to multiply for 2 to the x. Its derivative was 2 to the x times the ln of 2. The ln of 2 is slightly less than 1, which is why its derivative graph was below the original curve. For 3 to the x, its derivative was 3 to the x times ln of 3. Ln of 3 is slightly larger than 1, which is why its derivative graph was above the curve. Notice that this rule applies to any base, including when a is equal to e. If a was equal to e, then our derivative would be e to the x times ln of e, but ln of e is just 1, so we don't need to write it down. So this is like the main rule. This is the generalized form. This is just the special case. That being said, the vast majority of derivative problems that you'll deal with, whether it's IB, AP, or just anything in college, it's going to be about e to the x. E is such a special number. E to the x is such a special function. We're really going to be dealing with that far more often than we will be dealing with a to the x. Let's do some examples of that. So find the gradient function, that just means the derivative, right, for each of these 3. So first one, derivative of 2 times e to the x is just 2e to the x. And then for e to the negative 3x, it's e to the negative 3x. We copy it down, and then we multiply by the derivative of negative 3x, which is negative 3. We're not doing power rule here. This is not x to a power. This is e to a function of x. Don't confuse the rules. Second one, we've got a product here, right? This is x squared times e to the negative x. So we need to use the product rule. We'll do the derivative of x squared is 2x times e to the negative x plus x squared times the derivative of e to the negative x, which is e to the negative x, chain rule, times negative 1, because that's the derivative of negative x. Rewrite, just take that negative 1, change that plus to a minus, we're good to go. Third example, we've got a quotient now. So low-d high, high-d low, draw the line, square the low. Here it is. It's x times the derivative of e to the 2x, which is e to the 2x times the derivative of 2x. That's our chain rule. So we multiply by 2 minus e to the 2x times the derivative of x, which is just 1, all divided by x squared. I would just leave it like that. If you want to factor out the e to the 2x, that's cool. But, you know, whatever. 2 more examples. E to the x minus 1 cubed. We could expand that. Personally, I think that's too much work. Easier just to use the chain rule. For me, I'm not writing down all of this u stuff. I think that's an excessive amount of work. I would just say y prime is equal to, I know this 3 is going to come down for power rule, so it's 3 times copying the inside piece, e to the x minus 1. Finishing power rule, that's going to be squared, multiplied by the derivative of this inside piece. The derivative of e to the x minus 1 is just e to the x. Right away, I'm down here. If you like using the substitution with u, feel free. I just don't think it's necessary for these problems for me. This next one, it looks like a quotient, but I wouldn't think of it like that. Instead, I would rewrite this using a negative exponent for that square root in the denominator. So There it is. And again, I just want to show you my work. I can do this all in one step. It's power rule. So my negative 1/2 is going to come down. 2 times e to the negative x plus 1 stays inside the parentheses. My negative 1/2 exponent goes down by 1. So now it's minus 3/2. I'm going to run out of room on the board, but that's okay. I'm going to multiply this whole thing by the derivative of that inside piece, which is going to be 2 times e to the negative x. Oh my gosh, I need to use the chain rule again because the derivative of negative x is negative 1. So there's a double chain rule here, right? I've got the derivative of the inside piece, but then that inside piece has its own inside piece. So final answer looks like we're going to have negative canceling with a negative. And let's see if that matches what the book does. Again, they're using their whole U thing. And yeah, we're good. Oh, of course, the 2 and the 1/2 are going to cancel out as well. All right, let's jump to logarithms. This is in the data booklet. The derivative of ln of x is equal to 1 over x. We need to extend that to the chain rule, though. So the derivative of some function of x is going to be equal to, you might think of it as 1 over the function times the derivative of that function, but you can also just squeeze that into one fraction as the derivative over the function. Also in the formula booklet is this one down here. The derivative of log in any base should be equal to 1 over ln of that base multiplied by x. Again, this captures this special case, because if the base was e, then it would be 1 over ln of e times x, and again, ln of e is equal to 1. This rule, for whatever reason, is not in the textbook, but as I said, it is in the data booklet. And just like with exponentials, it's really rare that we end up having to take the derivative of a log of a base other than e, so shouldn't have to worry about it too much. But there it is for you. But before we do any examples, I want to call your attention to one thing about that first formula there, because you might have noticed that ln of x and 1 over x, they don't even have the same domain. So let's talk about that for a quick second. Here's a graph of f of x equals ln of x. Again, let's just make sure that this function 1 over x even makes sense for its derivative. What do the slopes of the tangent lines for ln of x look like? As we get closer and closer to 0, those slopes are getting closer and closer to positive infinity. As we get closer, as we get farther to the right, the slopes are getting closer and closer to 0. So yeah, that function, the y values of this function behave as the slopes of that function do. However, 1 over x has this whole other branch, which has no meaning when it comes to ln of x, because ln of x is not defined for these negative real numbers. And actually, if I were to not show that, but just ask Desmos what is the derivative of f of x, it's only going to show the positive branch of 1 over x. So a derivative should really only be defined on the same domain, at most the same domain as the original function. Actually, it could be defined on a smaller domain, but it could not be any larger of a domain than the original. More on that in a minute. Let's just look at a couple of examples first. So let's differentiate each of these. Chain rule is going to abound. This is so exciting. Okay, letter A, we've got ln of a function of x. So the derivative of that is going to be equal to, one way to do this, and the book is doing this, I think probably the easy way, would be to use, properties of logarithms to break this up. Since we have a product inside, we can represent that as a sum of logarithms, and then the derivative of ln of x is just going to be 1 over x. And then ln of e to the negative x, you can actually rewrite that as just minus x, and so the derivative of that's going to be minus 1. So that's pretty clever. If you didn't see any of that, then we'd go about this the other way, the long way, which would be to take the derivative of x times e to the negative x divided by x times e to the negative x. So the derivative of that would be product rule, x times the derivative of e to the negative x. The derivative of e to the negative x will be e to the negative x multiplied by -1 plus the derivative of x, which is 1, multiplied by e to the negative x. We then notice that a whole bunch of things are going to cancel here. Every term has an e to the negative x, so that gives me negative x plus 1 divided by x. And we could rewrite that as negative x over x plus 1 over x, which is going to give us the exact same thing as that over there. So I don't know. It doesn't really matter which way you do it. You're going to get the same answer. For letter B, we've got this massive thing. Again, yeah, in this case, I think perhaps property of logarithms might be helpful here. So we can rewrite that as a difference and a sum, and then just differentiate each part. Now all three of these turn into, well, this is 2 times 1 over x. This part's going to be 1 over x plus 2, and this third one will be 1 over x minus 3. It's all 1 over because the derivative of x plus 2 is just 1. The derivative of x minus 3 is just 1. So we can still think about chain rule for each of these. It's just that the added derivative we're doing is always 1 for each of these. And that's definitely easier than taking the derivative of this quotient and then dividing it by that quotient. God, that would be terrible. Now, our little friend from the book is reminding us of what I was saying earlier, that a derivative function is valid on, at most, the domain of the original function. It's not obvious from looking at either of these two original functions what their domains are. Those are fairly complicated, but it's at least something to keep in mind. And in this case, that function, if I just thought about its domain, it would be just x not equal 0. And if I thought about just the domain of this one, it's going to be x not equal to 0 or -2 or 3. But if we actually look at those two functions, we'll see that the domain of these derivatives would be quite a bit more restricted. So here's the original function is only going to be defined for positive x values. I guess that's easy to tell from this product. I need x and e to the x to be the same sign so that the ln of whatever's in the brackets is positive, but e to the negative x has to always be positive, therefore x has to also always be positive. So there's no portion for this graph that's hiding anywhere to the left of the y-axis. This is the only part. So really its derivative should also only exist to the right of 0. And then this other guy is a very complicated looking thing. I mean, Desmos doesn't even know what to do with it. Desmos is totally freaking out here. I mean, it's really just going up towards infinity there. And if we just graphed the inner part to that ln, we see that in between those two vertical asymptotes of -2 and 3, it is always negative. So we know that the ln of that function definitely does not exist in between those two vertical asymptotes either. So literally anything in between those two is out of bounds for this one. So these, you can't just tell the domain of the derivative by looking at the function itself. You really need to think about the original one. And here's actually just two more simple examples to illustrate this point. First one, absolute value of x. Clearly here the derivative is +1, here the derivative is -1, but what happens at x equals 0? I can keep zooming in forever, and really I'm just going to keep seeing a corner there. It's never going to smooth out. So there actually is no derivative at x equals 0, and its derivative graph looks, whoop, it's not in the picture right now. There it is. Its derivative graph is a horizontal line at 1, a horizontal line at -1, and they don't connect. It's actually not defined at x equals 0. A similar case is something like x to the power of 2/3. This is not technically a corner. This is actually something that we call a cusp. But it's the same problem. We have this sharp point that we're getting closer and closer and closer to. Clearly, as I get closer to 0 from the left, the slopes are getting closer to positive infinity. As I get closer to 0 from the right, the slopes are getting closer to negative infinity. And yes, its derivative graph does look like that. And you could use the power rule to think about what that looks like. You'd get a function that would be undefined at x equals 0. So the derivative graph is not defined necessarily on the same domain as the original function. It could be defined on a smaller domain, but it could not possibly be defined on a larger domain. Anyway, the main point of this video was to get used to the formulas for logarithmic functions as well as exponential functions, and just to remind you to watch out for the chain rule. Chain rule! Anyway, that's the end.